So we have problem number 8 in Advanced Classical Mechanics Practice Final Exam. So we have a particle of mass m moves in one dimension under v of q equals 1/2 m omega squared q squared plus epsilon q to the fourth, where 0 is less than epsilon is much less than 1. So part A, write the time-independent Hamilton-Jacobi equation. Part B, construct the action variable j equals 1 over 2 pi for this closed line integral p dq to first order an epsilon. Part C, find the perturbed frequency capital omega of j. Part D, explain the relationship between the Hamilton-Jacobi method and action angle variables. And part E, discuss the meaning of the frequency shift. So this is a Hamilton-Jacobi theory problem. So the Hamiltonian is h q comma p equals p squared over 2m plus 1/2 m omega squared q squared plus epsilon q to the fourth, where 0 is less than epsilon is much less than 1. And the time-independent Hamilton-Jacobi equation is h q comma partial derivative of w with respect to q equals e. So from here we could say 1 over 2m times the partial derivative of w with respect to q squared plus 1/2 m omega squared q squared plus epsilon q to the fourth, that's going to equal e. So from there, for solving for the reduced action derivative, so this would be partial derivative of w with respect to q, that equals p q comma e equals, this is the square root of 2m times the quantity e minus 1/2 m omega squared q squared minus epsilon q to the fourth. So the action variable is going to be j equals 1 over 2 pi. Moving along from here, sorry about that. So part B with the action variable is j equals 1 over 2 pi closed line integral p dq. So for the unperturbed harmonic oscillator, h naught equals p squared over 2m plus 1/2 m omega squared q squared, and the action variable is j naught equals e over omega. So we write the harmonic oscillator and action angles variables. So our q is equal to square root of 2j over m omega sine theta, and our p is equal to square root of 2m omega j cosine theta. So then building on that for the perturbation, so we wind up with, then the perturbation is h sub 1 equals eq to the fourth. So if we substitute now here, this q equals h sub 1, q is h sub 1 equals epsilon times the quantity 2j over m omega squared sine to the fourth theta. So h sub 1 is going to be epsilon 4j squared over m squared omega squared sine to the fourth theta. So our average over one cycle for the sine to the fourth theta, that's going to come out to 3/8. And therefore our average h sub 1 here is epsilon 4j squared over m squared omega squared times 3/8. Thus this average h sub 1 3 epsilon j squared over 2m omega squared. So to the first order in epsilon, the Hamiltonian action angle form is h of j equals omega j plus 3 epsilon j squared over 2m squared omega squared plus big O epsilon squared. And since h of j equals e, the energy action relation is E equals omega j plus 3 epsilon j squared over 2m squared omega squared plus big O epsilon squared. So isolating j in terms of E, j equals E over omega plus epsilon j sub 1 plus omega plus big O epsilon squared. So substituting into E, so we get E equals omega j plus 3 epsilon j squared over 2m squared omega squared. So to the first order, we get E equals omega times the quantity E over omega plus epsilon j sub 1, close parentheses, plus 3 epsilon over 2m squared omega squared times the quantity E over omega squared. So setting this equal to 0, 0 equals epsilon omega j sub 1 plus 3 epsilon E squared over 2m squared omega to the fourth. And isolating j sub 1 equals negative 3e squared over 2m squared omega to the fifth. So therefore we could say that j of e equals e over omega minus 3 epsilon e squared over 2m squared w to the fifth, over 2m squared omega to the fifth plus big O of epsilon squared. And building on this, the perturbed frequency is going to be capital omega of j equals dh dj, so derivative of h with respect to j. So capital omega of j equals d dj omega j plus 3 epsilon j squared over 2m squared omega squared. And capital omega of j equals lowercase omega plus 3 epsilon j over m squared lowercase omega squared plus big O of e epsilon squared. So in terms of the unperturbed amplitude A, we're going to have j equals 1/2 m omega a squared. So capital omega is going to be equal to lowercase omega plus 3 epsilon over m squared lowercase omega squared times the quantity 1/2 m lowercase omega a squared. So here capital omega is going to equal lowercase omega plus 3 epsilon a squared over 2m lowercase omega plus big O epsilon squared. Okay, so building on this, because epsilon is greater than 0, the quartic term makes the oscillator stiffer at large amplitude. So therefore, the frequency increases with amplitude. And the Hamilton-Jacobi method is related to action angle variables because solving the Hamilton-Jacobi equation gives a canonical transformation from QP to variables theta j, where j is constant for an integrable one-dimensional system and theta evolves uniformly, where such that j dot equals 0 and theta dot equals capital omega of j. So h of j equals omega j plus 3 epsilon j squared over 2m squared omega squared plus big O epsilon squared. And capital omega of j equals lowercase omega plus 3 epsilon j over m squared lowercase omega squared plus big O epsilon squared. And this agrees with the standard hardening oscillator result. Delta capital omega equals 3 epsilon a squared over 2m lowercase omega, and that's greater than 0. So the answer is internally consistent. All right, so that is problem number 8 of 15. Thank you very much and have a great day.